hey everyone. Okay, first thing before I forget, the chapter that I started this last time, I labeled it chapter 7, and you might be wondering what happened to chapter 6. Well, here's the thing, and I think I've mentioned this before. I'm trying to renumber all my notes, and so sometimes I forget. So we are in chapter 6, which is called what? Solvability by radicals, right? Yeah. So change that to a 6. And then that first theorem I did, the second isomorphism theorem, that should be theorem 6.1. And then theorem 6.2 is the third isomorphism theorem. Now, here's what we have in store. What we have some hard proofs that are coming up. But we're getting very, very close to our goal, right? Which is this connection or this result of Galois that tells us that in certain situations, there will be polynomials that are not solvable by radicals. Right? And so that's where we're headed. And so what we need now, this is a purely group theoretic result, right? There's not going to be any field theory going on here in this theorem. And this is pretty hard proof. At least it takes some, I don't know, there's a lot of details that go into this proof. So here we go. So let's let G be a group. So part A, if G is solvable and H is a subgroup of G, then H is solvable, right? So subgroups of solvable groups are solvable. The second part, so part B, so if our let's say that's fine. Okay, so if H is a normal subgroup of G, then G is solvable if and only if H and G mod H are solvable. Okay, so these are really the group theoretic, this is one of the group theoretic properties that is extremely important when it comes to our main theorem, right, on solvability by radicals of polynomials, right? This is the theorem that we're going to need multiple times in that proof. Okay, so let's prove this. Part A is not so bad. Part B takes some work. Okay, so let's see. And this is good. The details are worthwhile so that it sort of gets this idea of solvability ingrained in our mind. So so let's assume that G is solvable. So what does that mean? It means that we have a subnormal series with abelian quotients. So right, so then we have a subnormal series, so that would be 1 equals, right, that's the trivial group, equal to G0, normal in G1, normal in G2, dot, normal in dot, 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 normal in G sub n equal to G, where each quotient, so G sub I plus 1 mod G sub I, is abelian. And now what we need to do is construct a subnormal series for H that has abelian quotients, right? So we want to somehow make use of this. And the obvious thing to do, I think, right, is to just intersect H with each of these, right? And then show that that actually gives us a subnormal series with abelian quotients. So, so let's define H sub I equal to, which way do I want to write it? Well, I guess it doesn't really matter. G sub I intersect H. Now, what that does is, so then we have the series, so it'll look like this: 1 equal to H0, subgroup of H1, subgroup of H2, subgroup of dot dot dot, subgroup of H sub n equal to H, right? So this is our candidate for a subnormal series. So the first thing we're going to do is show that HI is always normal in H sub I plus 1, and then we'll show that the quotients are abelian. So let's see. So since G sub I is normal in G sub I plus 1 and H sub I plus 1 is contained in G I plus 1, we can apply the second isomorphism theorem. So, so we have H sub I, which is equal to, by definition, right, this is G, which way did I write it? G sub I intersect H, but it's equal to G sub I intersect H sub I plus 1. And this is normal in H sub I plus 1 by second isomorphism theorem. Okay, so we've got the normal part, which means that this is a subnormal series. And so now let's check the quotients. And say also, if I look at H sub I plus 1 mod H sub I, that's going to be equal to H sub I plus 1 mod G sub I intersect H sub I plus 1. That's isomorphic to G sub I times H sub I plus 1 mod G sub I. And this is sitting inside, so this is inside G sub I plus 1 mod G sub I. Right, so once again here we applied the second isomorphism theorem. Now, we know that this is an abelian group. So we have this isomorphic to a subgroup of an abelian group, which means that it's that it's abelian also. So since subgroups of abelian groups are abelian, we conclude that our quotient H sub I plus 1 mod H sub I is abelian, and so therefore H is solvable. Okay, so now let's prove part B. And so, right, this is an if and only if, so we got two directions to go. So in the forward direction, right, we're going to assume that we've got a normal subgroup. So let's assume H is a normal subgroup of G, and that G is solvable. Right, and then our goal, what we need to do is show that H and G mod H are solvable. Of course, we get for free essentially that H is solvable, right? So by, or let's say it like this. So then H is solvable by part A, right? So our goal now is to show that the quotient G mod H is solvable. So we have a subnormal series 1 equal to G0, normal in G1, normal in ... normal in Gn, which equals G, where each quotient Gi plus 1 mod Gi is abelian. And now what we need to do is come up with a subnormal series with abelian quotients for G mod H. Now, so here's what we want to do. So let's say consider the series, and it's going to look like this. So it'll be 1 equals H G0 mod H. Right, this is G0 is the identity or the trivial group, so H mod H, right? That's the trivial group. Subgroup of H G1 mod H subgroup ... subgroup of H Gn mod H. Of course, H times Gn is just all of G, right? And so this is G mod H. Right, so what we want to do then is show that we get normality all the way down the line and that the quotients are abelian. Okay, so first we'll show normality. So we first show that H G sub I plus 1 mod H is a normal subgroup of H. Oh, I want that the other way around. Sorry, that should be a Gi there. And then H Gi plus 1 mod H. And we're just going to use the standard normal subgroup test. So let's pick, say, X in H Gi mod H and Y in H Gi plus 1 mod H. So then what do these elements look like? Well, they look like cosets, right? So X is going to be H little g sub I times capital H, and Y equals some other, let's say H hat Gi plus 1 times capital H. For some H and H hat in capital H, little Gi in capital Gi, and little Gi plus 1 in capital Gi plus 1. All right, so we're just writing out what cosets would look like in this setting. And then I need to conjugate. So I'm going to look at YX, Y inverse. All right, so then YX, Y inverse equals H hat Gi plus 1 capital H, H Gi capital H, H hat Gi plus 1 capital H inverse. And so what do we need to do? We need to show that this lives inside that set right there. So let's see. First step, what do we know? So I think I want to flip them, right? Yeah, okay. So we know that H is a normal subgroup of G. So I can reverse the order of the cosets, right? I can write these as right cosets, and then all the H's, the little H's, will get sucked inside the capital H's, right? So this is going to be equal to H Gi plus 1 times capital H Gi times capital H Gi plus 1 inverse. And here, right, this is because H is a normal subgroup of G. Now I'm going to join this all into one piece, right? So just using coset multiplication, this is H times Gi plus 1, Gi plus 1 inverse. Now, if we look at this element right here, we know that this lives in capital G sub I. The reason is that capital G sub I is a normal subgroup of capital Gi plus 1. So we can say, so since G sub I is a normal subgroup of Gi plus 1, we have Gi plus 1, Gi plus 1 inverse is an element of capital Gi. So, continuing on here, this one, what I want to do, now I'm going to reverse it. So, H Gi plus 1, Gi plus 1 inverse equals, I'll pull that thing off there first. Yeah, I'm going to pull the H hat off there. So this is H hat Gi plus 1, Gi plus 1 inverse, which is equal to H hat Gi plus 1, Gi plus 1 inverse times capital H. And this lives in H Gi mod H. Thus, right, so I mean, there's really a string of equalities here. So what that means is that y inverse is an element of H Gi mod H. And so we have normality H Gi mod H is a normal subgroup of H Gi plus 1 mod H. Okay, so now we need to show that the quotients are abelian. So we now show that quotients, obviously of that subnormal series, are abelian. Okay, so what I want to do, so let's consider the projections. So I'm going to have, let's call it Q. Q goes from G to G mod H. And I also want a projection going onto each of those constituent groups from our subnormal series. So I'm going to call them Q sub I. We'll say and Q sub I going from H Gi plus 1 mod H to H Gi plus 1 mod H mod H Gi mod H. Okay, so these are the projections, so they send an element to its corresponding coset, right? And notice, this is the quotient that we want to show as abelian, right? Now, So then, if I look at Q applied to GI plus 1, that's equal to GI plus 1 mod H, which is equal to H times GI plus 1 mod H. And now I am wait, why is that? Okay, and sorry, I spaced out for a second right here. But I was thinking, why are these equal? Well, they're equal because, right, so why is this equal to this? They're equal because H is normal in G, which means if I take any element from GI plus 1, right, the corresponding coset, so let me in fact write this out. So if I took a little GH, that's equal to G, yeah, so I'm taking a GH in here, that's equal to something like this, a GH times H, which is equal to, say, H hat G times H, right? And this thing right here lives in the HGI plus 1, right? And vice versa, we can go back in the opposite direction. So, sorry, I spaced out for one quick second. Right, so now we have equality right here. And so, now what I want to look at is Q sub IQ of GI plus 1. That's equal to Q sub I, remember we're doing composition right here, so Q sub I of HGI plus 1 mod H. And the whole point, I needed these equal to each other so that then I could make sense of the composition right there. Right, so now this is equal to, so what does this do? This is going to give me HGI plus 1 mod H mod, let's make sure, is it mod? Yeah, HGI mod H. And so what this is saying, so here's the point. So in other words, Q sub I of Q restricted to G sub I, actually G sub I plus 1. Now where's that mapping from? It's mapping from G sub I plus 1, now I'm going to run out of room, aren't I? To H GI plus 1, oh man, sorry, mod H, mod H GI mod H. I guess I just barely squeaked by there. Anyways, this function right here is onto, right? So this is an epimorphism. Now, what I'm doing is I'm setting up an application of the first isomorphism theorem. So I need to identify the kernel also. So given, let's say, little x in gi plus 1, we have x in the kernel of q sub I of q restricted to gi plus 1, if and only if what? Well, qi of q of x equals, so let's see, what would it have to equal? It would have to equal this coset down here, so hgi q equals, oh, I'll say what it is in a second. Let's write this out. So what would this mean? This would mean qi of x. Where does this one go? Q's projecting onto a. Okay, g on a. So that's qi of xh. And then when we plug it into q sub I, we get x sub h times h gi mod h. And it's going to have to equal this coset, so h gi mod h. Now, and this is true if and only if xh is in h gi mod h. If and only if, okay, so what would that tell us about x then? That would tell us that x has to live in hgi. So if and only if x is in hgi. In other words, what we did is we showed that the kernel of this mapping right here is equal to h times gi. And we're going to say this a little bit fancier. Therefore, the kernel of the mapping q sub I of q restricted to gi plus 1 is equal to h times gi, which we're going to write this in a fancier way. gi plus 1 intersect h gi. I think that's how I want to write it. Yeah. Since gi lives inside gi plus 1, when we do this intersection, nothing happens, right? So, by the first isomorphism theorem, domain mod kernel is isomorphic to the image, or the image, which is let's write this correctly. H gi plus 1 mod h mod h gi mod h. And why the left-hand side? Oh, right. Okay, so now, yeah, let me label this one. Sorry, it's a little hectic here. So now what I want to do is apply, so I'm going to label this equation star, and now applying the third isomorphism theorem to the left-hand side of star, we get that this, and then I'm going to insert okay, so gi plus 1 mod gi plus 1 intersect h gi. We know that this is isomorphic, and so I'm going to put g sub i's underneath. Okay, so this will be g sub I plus 1 mod g sub I mod g sub I plus 1 intersect h g I mod gi. Okay. Now, we know that this is an abelian group because this is. So now what we have is we have the right-hand side right here is isomorphic to this abelian group. So since, and I don't even want to write this again, so let's call this one, this equation right here, let's call that double star. So now, or since gi plus 1 mod gi is abelian, so is the quotient on the left-hand side of double star. So now it follows that, yeah, fine, the quotient, so is the quotient on, yeah, okay, right, so that means that this is abelian, and so now this is, which that forces this one to abelian, so it follows that the right-hand side of star is abelian. Those are the quotients that we needed to show are abelian, and now we can conclude that our quotient g mod h is solvable. All right, so therefore, g mod h is solvable. So that takes care of the forward direction. Now we need to prove the reverse direction. So now we're going to assume that h and g mod h are normal, solvable. So assume that h and g mod h are solvable. And then we want to prove that g is then solvable. So now we have a couple of subnormal series. So then there exists subnormal series. So we'll have one normal in, I'm going to call these the h's. So h0, or no, I guess this is equal to h0, normal in h1, normal in h sub m, I think I used here, yeah, h sub m, which equals h with h sub I plus 1 mod h sub I abelian. And these ones are going to be k's. Okay, so 1 equal to k sub 0, normal in k1, normal in dot dot dot, normal in k sub n equal to g mod h with k sub I plus 1 mod k sub I abelian. Okay, now somehow we need to piece these two together in a way, piece them together or make use of these to build a subnormal series for G. So here's what we're going to do. So let's let Q from G to G mod H be the projection. And then yeah, for each one, and define G sub I equal to the inverse image of K sub I. Right? So what that does then, it takes this normal subgroup and it pulls it back and gives us one in, it gives us a subgroup in G. So note that. So there's three things that I want to observe. The first one is that G0, right, that is the inverse image of K sub 0, which is equal to the identity in G mod H. Well, the identity in G mod H is just H. All right, so this is equal to H. The second thing is what? Gn, that's equal to the inverse image of K sub n. And that's equal to all of G, right? So this is the inverse image of G mod H, which of course is equal to all of G. And then the last thing is we know that we've got subgroups all the way through. So G0 is a subgroup of G1, subgroup of G sub n, which is G. Okay, now this is nice because it's going to allow us to piece things together. So notice what we have. Starting at the identity, we get to H, which is G0, which goes to G. Okay, so we can glue this one together with this one, and that's going to turn out to be the series that we want. So, so we say now, consider 1 equal to H0, normal in H1, normal in dot dot dot, normal in H sub m, which equals H. And H is equal to, right, H is equal to G0, which is then contained in contained in G1, contained in G2, dot 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 dot. contained in Gn, which is equal to G. Oh, and let's see, is this true? If H is a normal subgroup of G, which means that it will be normal in G1. So I actually get to put a little normal symbol right there. All right, if you conjugate by anything in G, you get H back. If you conjugate H by anything in G, you get H back. And so in particular, if you conjugate by elements of G1. Okay, so what do we need to do then? We need to get normality here, and we need to get abelian quotients here. I wish this thing wasn't quite so long, but oh well. Okay, so let's so now let X be in Gi and Y be in Gi plus 1. Then if I do conjugation, right, Y X Y inverse, oh, actually I'm going to hit it with Q, right, so then Q of X, Y, no, Y, X, Y inverse is equal to, let's split this up, so this will be Q, Y, Q of X, Q of Y inverse. Now let's see, where does Q of Y live? Q of Y lives in K sub I plus 1. So both of these, so these are in Ki plus 1. That one and that one. And then this one lives in, so this one is in Ki. And we know that Ki is a normal subgroup of Ki plus 1. So this is in Ki, all right, because K sub I is a normal subgroup of Ki plus 1. Well, okay, so that means, so therefore, YX, Y inverse is in the inverse image of Ki, which is equal to G sub I. And so that gets us normality, right? Gi is a normal subgroup of Gi plus 1. Okay, last piece, we need to look at the quotients. And we're going to do some third isomorphism fanciness now. So so now Ki plus 1 mod Ki is isomorphic to Gi plus 1 mod, get this right here, H intersect Gi plus 1 mod Gi mod H intersect Gi. Now, why is that? Because Ki, so let's write this down. Right, because Ki is equal to the image of Q restricted to Gi, and the kernel of Q restricted to Gi is equal to H intersect Gi. So what that's saying then is that Ki is isomorphic to that piece. Ki plus 1, by the same reasoning, is isomorphic to that piece right there. And now this intersection, these intersections are both equal to H, right? Because H lives inside both of these. So so this is equal to Gi plus 1 mod H mod Gi mod H, and this is because what? Oh, right, because H lives, yeah, because H is contained in Gi, all the Gi's, right? So when you do the intersection right here, right, you get just H, right? Because H lives inside here, H also lives inside here. Just thinking about how our subnormal series works. Or I guess I can't call it our subnormal series. But our H, right, is contained in G, how'd it go? H is equal to G0 contained in G1 and so on. So H lives inside all of these. Okay, now this is third isomorphism theorem. This is isomorphic to Gi plus 1 mod Gi. All right, so this is third isomorphism theorem. Okay, and so what now? We know that this is abelian. So since Ki plus 1 mod Ki is abelian, so is Gi plus 1 mod Gi. That's what we needed, so we can say, therefore, G is solvable. So therefore, G is solvable. All right, so that completes the proof, and I think that's enough for today, so we'll pick up with this next time.